Welcome back to lesson 2 on energy. And in this lesson, we're defining two brand new terms, a concept called the system and a concept called the surroundings. Now, you guys will recall that when we talk about energy in terms of chemistry, all right, we can break down the types of energy in chemical systems into two things. Chemical systems. We pretty much have two categories. All right, one of which has to do with chemical reactions, which is not going to be the main focus of what we're talking about today. But I want you to know we're not excluding them, and they basically, once we understand the definition of system and surroundings, then we're going to apply these two concepts to chemical reactions as well. But the main thing where we're going to start today has to do with physical changes. All right, physical changes. And I'm going to focus on a physical change that I think hopefully is obvious to everyone. And that's what happens to an ice cube when we take it out of the freezer. All right, and common sense dictates that if we take this thing out of the freezer, and I'm going to assume, because we need to start somewhere, that we literally have the ice cube at 0 degrees centigrade. This is the freezing point of water. Although your freezer is going to be much cooler than that. It's going to be running around minus 20. But we'll say that we pull this ice cube out. And then common sense dictates that if you're pulling this thing out of the freezer in your kitchen, which is warm, that the ice cube is going to melt. So this is a physical change. All right, and I will write it correctly in chemistry lingo to look like this. So we're going to go from H2O solid to the H2O liquid, and this is the melting process, so let's just write that in here. This is the melting process. All right, so we have this ice cube and we're going to melt it. All right, so the main point today is to get familiar with this designation of system versus surroundings. So the thing that we want to focus on here is what happens to the ice cube, and that makes the ice cube our system. All right, and we pulled the ice cube out of the freezer and we moved it into the kitchen area, which is warm, and so therefore we would call the kitchen area the surroundings. But what I want to do is diagram this a little bit more carefully. So I'm going to go ahead and draw a picture down here. All right, and it's going to be composed basically of two circles. All right, and on the inner circle, we're going to put our ice cube in here. I'll just draw it as a square. Well, I think I can get the whole thing in. All right, so here's our ice cube, and this is our system, so I'm going to abbreviate system as SYS. And our system is cold. All right, I'm going to use the word cold here. That should make sense to you because you pulled the ice cube out of the freezer, and like I said, we're going to assume it's at 0, even though we know it's actually a little cooler than that. And then what we're going to do is we're going to take that ice cube and we're going to place it into a glass of water. All right, and so this is H2O liquid, and then here's the ice cube. And because what I'm trying to do here is be abundantly clear about what's going on. All right, so the ice cube, which is cold, is placed into a glass of water, which is warm. All right, now the water is about room temperature, which you guys should know from over the course of the year is around 25 degrees centigrade. If you're a Fahrenheit person, this is going to be around 75 degrees. So basically, the liquid that is surrounding the ice cube is warm. All right, and so let me enter that here in this circle. So this is our H2O liquid, It is about 25 degrees C, and we're going to call this now our surroundings. And I'm going to change color for this. So the inner circle is our system. All right, and the surroundings are warm. We're going to call this a hot body. All right, and the terminology here comes from thermodynamics. So this is a hot body, and our system we're going to call a cold body. Now, common sense dictates that the ice cube is going to melt, and the reason for that is because the surroundings are warm relative to the system, and energy is going to move from the surroundings, all right, into the system. So I'm gonna do this way. Whoops, I made a mistake. Let me just switch that. All right, so what's going to happen here is that energy, we're going to talk about what kind of energy this is in a minute, moves from the surroundings, and I'm using a negative sign to indicate direction. Where does the energy go? It ends up going into our system, which is the ice cube. And because energy is coming into the ice cube melts. All right, now let's go ahead and change to another screen. So let's diagram this a little more carefully. All right, and so what I'm going to do now is use a square to indicate our system and our surroundings. So we're going to call this the ice cube. All right, and connected to that is going to be the H2O in the glass. So this is H2O liquid. This is the glass. This is the ice cube. And the ice cube is cold. All right, and the liquid surrounding it is hot. So let's talk about what this means. All right, so in a liquid, if any kind of a substance, actually any substance, let me put this up here. So any substance, all right, any substance with a measurable temperature I'm going to watch out for my spelling. I'll probably make some errors here. Any substance with a measurable temperature has kinetic energy, which I'm just going to abbreviate. Now, think about that for a minute, and let's come back down here to our example. So in the diagram I drew on the other page, we have two rings. All right, out here is my surroundings, and in here is my system. The system is cooler than the surroundings. So the ice cube, which is at 0 degrees centigrade, and then remember, the glass of water is at 25 degrees centigrade. All right, think about that for a minute. Which of these two things has got greater kinetic energy? So the liquid surrounding the ice cube, I'm going to call kinetic energy prime. Right? The liquid surrounding the ice cube, because it's at 25 degrees centigrade and has a higher temperature, it's going to have a certain amount of kinetic energy associated. Remember that kinetic energy is the motion of the particles, and we learned that your molecules have two kinds of motion. There's vibrational and translational. The ice cube, on the other hand, we're going to call this, let's see, I'm going to use, change the color here. The molecules that are frozen in there, right, all of the water molecules are attached. They also have kinetic energy, but because this is a solid, right, until it gets melted, the kinetic energy that's in here is vibrational, whereas the kinetic energy over in the liquid, right, that's out here. This is going to be Ke prime. And the Ke in the system, we're calling, let me get that color straight so it correlates, is just Ke. Now, if you think about it, and this goes back to stuff that you guys have learned over and over again for a long time. This is the solid form of water, right? You should know at this point it has less kinetic energy than the liquid. So it's valid for us to write the following equation, if you will, that the Ke prime, all right, is greater than the Ke of the solid. Now, what's going to happen in here? So you have this liquid surrounding the ice cube, and all of the molecules are vibrating and they're moving translationally, or in a translational sense. The water molecules of the liquid are having collisions with the ice, and as those collisions occur, eventually the ice cube itself, the water molecules that are locked in place in there, are going to begin vibrating and against one another with the same kind of frequency that you have in the liquid. And what's going to happen is that system's going to begin to warm up. And as those molecules in the ice formation begin to vibrate more violently, we're going to start breaking bonds between the H2Os, and this thing is going to transition to a liquid, and that's why the ice cube melts. The main point is that we're going to have energy, this kinetic energy moving, and I'm going to show it this way. We're going to have energy, and I'm going to use a negative sign to indicate direction. So it's leaving the hot body and it's moving to the cool body. So kinetic energy is basically going to be transferred from the warmer liquid to the ice cube, and eventually the ice cube's going to melt. Now, this transition, so we have energy moving from the surroundings. Let me go ahead and write that down. In this scenario, we have energy moving from surroundings, which I'm going to abbreviate, to the system. Whoops. To the system. And I'll abbreviate that. So energy is lost by the surroundings and exactly gained by the system, right? And when I say that the surroundings lost energy, I'm not suggesting that it went off into the ozone somewhere. It was exactly transferred from this compartment to the ice cube, which is what we're calling the system. So we have a name for that. For the system, the energy transfer was what we call endothermic. Endothermic, because this system gained energy. All right, and for the surroundings, we call this process exothermic, because this system lost energy. This surroundings lost energy. I'm sorry if I don't want you to be confused. So the surroundings here is losing energy, okay, and our system gained energy. So for anything that is gaining energy, this is an endothermic process. And for anything that is losing energy, that is an exothermic process. All right. Now, one last thing to mention. We've already established the kinetic energy of the water that was in the glass. Okay, this is our surroundings. Is at a higher level than the energy of the ice cube, of the molecules in the ice cube. So the energy of the liquid had a higher kinetic energy to start with than the kinetic energy of the ice cube. At the end of this process, all right, at the end of the process, so after ice cube melts, let me put some words on this. So after ice cube melts, all right, comma, kinetic energy of the system and surroundings equalizes. So KE is the same for both. All right, that's important. Now, one last connection. All right, I established here that the kinetic energy of the liquid at the beginning of our experiment was at a higher level than the kinetic energy of the ice cube. So our glass of water was at a higher potential energy, a higher potential thermal energy. All right, than the potential energy of the ice cube. So to get an equation out of this, I'm going to pull this over here. PE of the liquid at the beginning of our experiment is greater than PE ice cube. All right, and with that, I'm going to go ahead and finish the video. Thanks for watching. If there's something here you didn't understand, what you need to do is literally watch the video over again, and you do that until you get it.